I'm just because apparently I'm not the host. But I just clicked on the link. Um,
Ah, maybe you were not signed in. Anyway, we are now
maybe I'm
recording
not
this
signed in.
important
Yeah,
conversation.
this is all right. Uh, so um, I've got I should increase the font size on that. Let me just do a quick share of this uh, nice big empty space. Um, right. Uh, so let's uh, we're going to be doing a bunch of stuff using Ask Bot. It's going to be uh, in new ways, and hopefully in ways that might actually kind of connect and make sense of what we did last semester uh, uh, somehow. Um, so remember what we were doing last semester was writing programs. I'm going to write a program. It's a very simple program. Um, there we are. So this program is called ID for identity, and it says um, uh, that for any type, so yeah, the type, the lowercase a, things that are lowercase are, stand for other stuff. They're not a thing in themselves. They're variables. So that this is the ID. This is the name I'm choosing. Has type A arrow A, and that means whatever type of thing you put in, the same type of thing will come out. Um, so here's my task to actually define what this function does. And guess what it does? It does nothing. If the input is X, the output is also X. So the input is something of this hypothetical type A, and the output is the same thing, and it has the same type. So that's a definition of a function. I'm going to define another function, which I'm going to call compose. Um, and this is a thing which plugs functions together. So if we have a function from A to B, so if we know how to turn an A into a B, and if we know how to turn a B into a C, then we can put all that together and turn an A into a C. Um, uh, Red's been at the Emacs mode, so we've got uh, some more nice highlighting going on, at least uh, if you're using Ask offline with editor support. Um, so F is my A to B, and G is my function from B to C, and this A is the input here to the function I'm supposed to be building, and the output that I'm supposed to be delivering, I better have type C. Well, what can I possibly do? Uh, the only thing I can do with my A is to feed it into F, and that'll give me a B. So far, if I say F of A, I will it'll moan at me, not terribly helpfully. But f of a, f can take a as an input and give a b, and to go the rest of the way, I need to do g to the output of that. G will take the b that comes out and turn that into a c. So the whole thing will get us from A to C. And that's an acceptable definition. This is about essentially, this is plumbing, right? Um, there's uh, uh, there's this is just like a piece of pipe where whatever you put in one end comes out the other end. And this says if you've got something that turns A's into B's and something that turns B's into C's, we can plug them together and turn A's into C's. Okay, so that's programming, um, but whatever goes for programming also goes for explanation. Are you ready to grab this, Fred?
Yeah.
Um, I will just fling this in Mattermost. Um,
Um, Connor, can I ask if you can explain the define compose just again?
uh, I'll try. And just so here,
Mhm,
for any three kinds of thing, A, B, and C,
mhm.
we have we're given an f, something called f, a function called f, which can turn an A into a B.
Ah, okay, so that represents that.
Yeah, and a function called g, which can turn a B into a C.
Mhm.
So if you do one after the other, you should be able to get all the way from A to C.
Yeah.
And that's what we're doing. In comes our A. I do F to A to get a B. And then I do a G to the result of that to get all the way to C. So it's
Uh,
just, so it's uh, it's just plugging two components together. It's like if you have um, uh, you know, I have a dongle that turns USB-C into HDMI, and I have
huh?
a a cable that connected to a projector that turns an HDMI signal to a picture on the wall. I put the two together, and I can project my what's on my screen. Um,
Wow. Mhm.
this is just plugging two things together.
Maybe Connor, you could draw a little ASCII diagram.
Yeah, so maybe I could. Um, so um, here's uh, maybe I'll so I've got like uh, a box, feed A into my box F that
Mhm.
turns A's into B's, and out comes a B.
Oh, it's like an output. It's like a process.
Yeah, and uh, I feed the B into my next box, which is G, and out comes a C. Um, uh,
Okay, so A goes feeds into B into F, and that becomes a B, and then the B goes into G, which becomes a C at the end.
yeah,
Oh, that
uh,
makes sense.
yeah, and then this thing, uh, right. So here, these name choices are arbitrary. You know, I chose to call the first function f and the second function g, and I called the input a, not because I have to, but just to remind you that its type is a.
Mm.
So here I could actually do the same thing and just change that to a. And what's going on here is that there's no f in box. There's just a piece of wire. You feed an A in, and nothing's happening. The same A comes out. You know?
Yeah.
Uh, 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 yeah. Uh, uh, so that's the technology we were working with last semester. We were writing programs, writing functions that take inputs and produce outputs, and we were proving stuff about those programs. The stuff we were proving was all equations. Uh, but um, uh, there's more to logic than just this equals that. And we're going to spend some time at the beginning of this semester explaining um, you know, broader aspects of logic. Um, well, then the question is, is there more than programming? Um, I'm going to invite Fred to show you a more logical view at this point. I'll hit stop share. You good, Fred? You might want to turn your mic on.
Oh, that helps. Yep. So I've copied Connor's definitions, and I've even renamed things to be the same. So I'll just show you some other things you can do in Ask, and then I invite you to compare what I'm doing with what Connor just did and see if you can see any similarities. So there's another keyword, which is prove, that you've seen. And as Connor said, I understand you've been proving equations last semester, but we can also prove implication, that one proposition implies another proposition, right? So let's see if we can prove that if we have a proposition P, then that implies P. So this says if P is true, then P is true, right? That seems plausible to me.
So P stands for something that you could fit after I wonder whether. And given such a thing, you can form the proposition P implies P. In other words, if P is true, then P is true. Do we believe this?
Yeah, so I wonder whether if P is true, then P is true. And let's explore if this is the case, right? So this is trying to prove an implication between two things, right? And the standard way of proving an implication is to use a logical rule, which is called implication introduction. So I want to introduce a proof of an implication. So I'm going to say by implication introduction with an L here, I guess, right? Okay.
There's no L.
There's no L. Okay, so I type that, and then I'll send that to ask and see what comes out. And there might be some more steps. I'm just going to do this little by little, right? But in this case, there are no more steps, because ask can figure out that, well, given P, there is a way to prove P, right? Anything else to add to that, Connor?
Yeah, so why don't you show what happens if you try and prove a general implication that P implies Q?
Right.
Yeah. Um,
Right. So let's say that I want to prove P implies Q. Okay. So I can say, okay, the standard way to prove this is by implication introduction. I'll send that. And then ask says, okay, in order to do this, you're now given that P is true, and you have to prove Q, right? So in this case up here, we were given that P was true, and we had to prove P. And because that's literally the assumption we had, there's no more sub-goals to prove, because us can just figure out that given
So,
P is true, right?
yeah, it's once again as ask is sometimes a little bit, at first anyway, too subtle and clever for its own good. It won't ask you to prove something that has already been given. So that's why the mere statement of, implication introduction for P implies P just goes through immediately. Once it's given P, prove P, that's done. Right, you're going to need to comment out the P implies Q.
It's going to delete it, but it's probably better to just comment it out.
Yes. But that's the
okay.
general shape of a proof of an implication. Is, how do you prove an implication? You just assume that the thing left of the arrow is true and try and deduce the thing right of the arrow from it.
Yeah. Okay, so another thing we could try to prove is something that's in Latin is called modus ponens. And it's saying that if I know that P implies Q, and I know that Q implies R, then I know overall that P implies R, right? So if it rains on a Monday and today is a Monday, then it rains today, right? Okay, so how do I prove this?
Is that modus ponens?
Yes.
Up to
Well, it's a special case of modus ponens, I guess.
Yeah.
But yeah.
Yeah,
Anyway,
sure.
it's a bad idea to think of these things in terms of Latin names rather than just what it is down to earth. So, okay. So how do I prove this? Well, so far I'm not really thinking, because I see that I have to prove an implication, right?
Yes, that's the arrow on the left is
yeah.
So
So that's another thing that's good to point out, maybe, that there's two ways you could bracket this, right? And just by convention, because it's most convenient, this really means bracketing things this way, right?
yeah, same as with the type of compose, actually.
Yeah.
Is that arrow groups to the right.
Yeah. But okay, so I see that I have to prove an implication, and there's a standard way of proving an implication. I do it by implication introduction, right? So I send that to ask, and then I'll see what I get back and see where we are. And then maybe at some point I'll start thinking. But so far it's basically mechanical, right? Okay, so I send that to ask. Ask says, okay, you're allowed to assume that the assumption is true. So given that P implies Q, and then you have to prove the conclusion, right? Which is this. Okay, and then again, I say, well, I'm asked to prove a conclusion, an implication. So I'm just going to say, well, there's a standard way to do that. You do it by implication introduction. Okay, so now I'm allowed to assume that Q implies R is true, and I have to prove the conclusion, but that's again an implication. So I'm just going to do it by the standard way we can do this. Okay, so now I'm allowed to assume that P is true, and I have to prove that R is true, right? And there is no standard way to prove R, because R is some proposition, right? We don't know what this is. But I am allowed to use what I've been given in order to prove this. So how can I prove R? Well, I have been given that Q implies R, right? So if I say from Q implies R and try that, then R says, well, okay, you know that Q implies R, so it's actually enough to prove Q in order to deduce R, right? Because we know that Q implies R. So now I've reduced the goal to proving Q. Okay, and do I have any way of proving Q? Well, I've also been given that P implies Q, right? Let's say from P implies Q. And then I have been given P, so ask is clever enough to see that actually P is already true, and everything is proven.
Right. Okay, so what's going on here is that we can work in two ways. When you look at what you're trying to prove, there might be some rules. So far, last semester, the only rule we saw was the root rule, right? You used to say by root, but there are other things you can go by depending on what you're trying to prove. So by root is a particular way of proving an equation. By imp I is how you prove something with an arrow in the middle. That stands for implication introduction. You will always, by the way, have access to the documentation that tells you the names of these things. So don't worry about having to remember a whole litany of rule names. That's documentation that will be made available to you. So here you see the goal is an arrow and implication. So you use by to make progress on the goal as stated. Meanwhile, this from thing basically says, how can this thing I know help me with my problem? So from works no matter what you're asked to prove. From says, whatever you're trying to prove, what use can I make of this assumption? So remember when you were programming, you used to do from on inputs to see how that input came about, what value it had. So learn more about, so from is always, how does this help? Whether you're proving or programming. So here it's, I'm trying to prove R. How does Q implies R help? Well, it helps by saying it's enough to prove Q. But what do you notice about the two things that Fred's proven compared to the programs that I wrote?
Their implications, is that what different?
Well, if you look at the types of the programs versus the goals, that we programmed with.
It's not so much about what's different about, rather than what's the same, right?
Yes.
But this looks very similar to this. This says, if you have an A, then you have an A. This says if P is true, if you have that P is true, then you have that P is true, right?
Yeah, and we didn't really need to do anything much.
Right, you can imagine that it's the same proof here and here, right? Just like it's the same element here and here. And this is saying, well, if you know that P implies Q and you know that Q implies R, then you can plug these proofs together and get the proof that P implies R, right?
Yeah. So that's the thing. The way to think of an implication like P implies Q is that what you're saying when you assert P implies Q is that if somebody gives me evidence for P, I will deduce from that evidence for Q. So a proof of an implication is a program that takes evidence for the hypothesis and turns it into evidence for the conclusion. So this is a radical departure for CS103 is that normally we leave it until 4th year to drop the big secret that programming and proving stuff are the same thing. But we thought we'd just tell you straight away this year.
Should I hand back control to you, Connor?
I think you possibly should. Let me bring back my Emacs. You could. I don't think. Well, okay. It's more important that I send you stuff than that you send me stuff, because
Yes, that's true.
of the way
It's
we're
also nice if there's a record.
playing this game. So I will hit share on that thing. Okay. So do you remember we had, I'm trying to remember, well, I do remember this much. We had a tutorial where I defined a type called both, where both A, B, where little a and little b are any type you like, stores a value of type A and a value of type B. And then I asked you to write a program which was something like let's actually use the word soak both. If you have 3 things grouped with the A and the B together and then the C on the side, you can group them the other way around. Okay. And we said we can use so we know that X has this type. It's made with it lives in type both, so it must be made with pair. So if I say from X, I will find out Ask will choose terrible names, but I will choose to call them A, B, AB, and C. And then AB must have this type, and C must have that type. So I can say from AB and discover that AB is also a pair of an A and a B. And then I need to make something of this type. So I have an A. And I can make a pair of a B and a C, so grouped the other way. And Ask is happy with that. So this idea of kind of being able to pair up values from 2 types. So like maybe A is a number and B is a formula or something like that. Could be anything. It's just saying if we've got a collection of 3 things grouped to the left, we can have 3 things grouped in pairs to the right instead. So all we're doing is rearranging grouping, keeping the actual values the same. So It's 5 to 10. So I suggest that we take a 10-minute break, and that Fred can show us something something logical that's not entirely unlike this program. Think about if you've ever encountered any logical operators that this might have something to do with. What do you expect to see happening here? But, I will paste this into Mattermost. Right. Okay, so yeah, let's reconvene at 10:05. I'm just gonna stay in the Zoom, but I'm gonna hit mute and switch my camera off.
Yeah. I'll leave the recording on just for ease of use. So.
Yeah, sure. I'll stop sharing. I guess I should do a Mattermost thing. Just making myself some toast, so which I didn't quite manage to fit into the 10-minute break. So if I disappear off camera, it's because something's on fire. But I think it's Fred's go.
Yes. Right. Are we ready to start?
Well, give it a minute.
Yeah.
In fact, I'll go and get me toast.
Start when you're back.
One thing that's worth worrying about in a storm is whether the electricity is going to stay up. So I spent last night cooking things that would be all right cold.
Such as toast.
Right. The fact that I can toast is just a bonus, right? It's bread. It works. Okay, we're probably in go condition, Fred.
Yeah.
Yeah.
Yeah. Okay. So let's get started before.
Before the electricity goes off.
Yes.
I'm going to turn my camera off because you don't want to watch me eat this toast.
Okay. So again, I've copied in what Connor did, and I'm going to show you something which might not be completely unrelated, right? So I'm going to prove something, and in general, I'm going to show you this kind of proposition which says that P is true and Q is true, right? And if I send this to ask to say, what does it mean to prove this? Well, then that's okay. There's nothing else. And the canonical way to prove it is, again, to use the introduction form for this thing. So I can say by and introduction. And if I send that to ask, then ask will say that, well, you have two sub-goals. You have to prove P and you have to prove Q, right? So to prove P and Q means that you prove P and you prove Q. Where the first and is this formal and the second one is and in English, right? And similarly, so that's how you prove P and Q. But if someone gives you P and Q and you want to prove R, well, then The standard way to prove an implication, we said, was by implication introduction. So we are given P and Q, and we want to prove R. Then we can say from P and Q to take it apart, right? And in this case, right. So then we are, rather than being given this composite thing where we have the proposition P and Q, that's one thing. We're now given the pieces. So we're given P and we're given Q. And then we have to take these pieces and actually put them together again to prove R somehow, right? So this is how we introduce a proof of P or Q. We use the AND introduction. And by using from, we can take it apart and we get access to the components. So let's see if we can prove something such as A and cheat.
Before you move on, Fred, what is
Yeah.
the difference between P and Q implies R and P and Q implies R? The possibility of and implies.
Sorry, you're
Find
saying
the brackets.
Yeah.
you're saying what's the difference between this and this? Is that right?
No.
No.
What's the difference between P and Q implies R, or P and
Oh, you're
Q
saying
implies R?
there's this.
Yeah.
You have to write it in the comment. So there's this, and there is this. That's what you're saying?
Yes. And in particular, which one is the above?
Right. Yeah. So we can see that I started the proof by implication introduction, right? Which means that this one must have been the one where you're trying to prove an implication, which is this one, right? But it's a good point. It's not at all obvious that it should be this way. It's just a convention, right? But by convention, this binds stronger than this. So this really means put the brackets like this, right? But yeah, that's a good point. And because these mean very different things, right? This says that if you know that P and Q are true, then also R is true. Whereas this means that P is true and also Q implies R, right? So this says that P is true, whereas this here you just get to hypothesize that P might be true. And if it is, what are the consequences of that?
So this and symbol, it's like an and gate.
Yes, because to make this true, you have to make both true. Just like to make the AND gate output a 1, you have to make both the inputs 1, right?
Okay.
Yeah.
There's a subtle difference between logic gates from 106 and the logical operators you see here, but the intuition is very much the same, and that's not an accident.
Yeah.
I'm very happy to say that it's like an AND gate. It's not exactly an AND gate, but it's very much like an AND gate. Okay, but let's see if we can give a concrete example. Well, concrete-ish. So if I know P and Q, and I also know R, then I would like to prove that I know P, and I also know Q and R. Okay, so how would I do this? So this is saying I know 3 things, but I bracket them up one way, right? So I know that P and Q is true, and I also separately know that R is true. And here I just packet things up the other way. So I know but the P is true, and I also know that Q and R is true, right? Okay, so again, I can get quite far without thinking, because I just see that I'm trying to prove an implication. So I'm just going to say, well, I know how to do that. I use implication introduction. Okay, and then I get to assume that this is true, and I want to prove this, right? Okay, and then again, I don't really have to think, because now here I'm given an assumption which tells me that 2 things are true. So I might as well just take that apart and say, from this, I want to derive my goal. So now the difference is that now I've been given that the first bit is true, and I've been given that the second bit is true, right? But then again, here I've been given an assumption that two things are true. So I might as well postpone thinking for as long as possible and just say, okay, let's take this apart as well. So now I get to know that the pieces are true, PQ, and up here I know that R is true. So I should now know that P is true, and that Q is true, and that R is Q, right? And a little bit unhelpfully, perhaps, ask knows how, just like it knows that if I don't put any brackets in here, it brackets this way. It also says that if you don't put any brackets between multiple ands, then it's going to bracket this way, right? So it didn't print these. But I guess we can put them in if we want ourselves, right? Just to make it clear. Okay, so I've taken apart everything as much as I can. And now the other canonical thing I can do is I'm trying to prove a conjunction, right? So I'm trying to prove this and this. And the canonical way to do that is to say, well, I'm going to do and introduction. So I'll do that. Okay. And then up here, when I did an and introduction, I had to prove both of the goals, right? Here I only get given one goal because the first goal is to prove that P is true, but I already have given that P is true, right? So ask doesn't ask me to prove this trivial thing. This thing is not completely trivial because I don't have given Q and R anywhere in all of my assumptions, right? But I do have given Q and I do have given R. So if I do another and introduction, then actually the two sub-goals I have here, which was to prove Q and to prove R, they are both trivial because I'm given Q and I'm given R, right? So what I did was I started with, I'm proving an implication. So I started by an implication introduction. Then I took my assumptions and I just made it into the smallest pieces I could by doing from on all of the ands. And then I put things back together again with an and, two and introductions, right? What do you think of that, Connor?
Well, I think that's pretty cool. I'd quite like if we could see the program and the proof on the same screen full. Just move that somewhere else, but it's good stuff, so don't delete it. Right. So you see what's happening. The implication introduction is the same thing as having the input on the left-hand side of the program, right? There's the X there on the left saying, we're going to get the input so we can look at it. That's what implication introduction is doing. And then the from that takes the input apart is saying, oh, what use can I make of this assumption? So, we take the whole thing apart and we get two pieces. And then we take the left piece apart. And now we've got all three separate pieces. And then we reassemble those pieces grouped slightly differently. But it's the same deal. And, good work noticing that this is an awful lot like the AND gate that you see in digital logic. Except what's going on there is testing. So the marvelous thing about the digital logic situation that we have inside our processors is that the electronic signals that we're working with are either 0 volts or 5 volts. And it's always possible to tell the difference between 0 volts and 5 volts. So the way you test if two signals are both at 5 volts is to feed them into an AND gate. If what comes out is at 5 volts, you're happy. Whereas here we're talking about proving. So it's, you know, there are things that we might consider trying to prove that are not just directly testable, not as easily as, you know, what voltage is this wire at? But the idea is the same, namely to prove a conjunction, to prove P and Q, you have to prove both pieces. And if someone hands you, if you're, how do you use such a proof? Well, if you know that both things are true, then you know they're true individually, and that's just the game we're working with, you know, the stuff we're working with. But you can see what goes in the program is what goes in the proof. It's the same basic machinery. Okay. So I guess it's my go again. And I wonder if you can guess what's going to come next. I see. Yes, so we also had this thing. Oh, I should share, shouldn't I?
Yes.
I should share. I should just type to myself. I should type to you. We had this type, which again is parameterized by two kinds of values. We said, well, you know, we have a value of type either A, B is either the left constructor packing up a value of type A, or the right constructor packing up a value of type B.
Like an OR gate.
So yes, that's you're seeing it coming, and that's very good. So let's just by way of tidiness, write something very similar to what we had a moment ago, which is that if I either have either an A or a B or a C, I might just as well have either an A or either a B or a C. Okay, so we're playing the define game, and I've grabbed hold of my input and temporarily called it X, and I got to decide how to deliver an output. So I need to get more information from the input to figure out how to do that. So I say from X, and I get two cases, which with badly chosen names. And on the right, if I know I'm in the right case for the input, I know I've got myself a C. So I'm ready to say the output is, well, it's definitely not an A, so I'm going right. And it's definitely not a B, so I'm going right again. And it is a C. Story so far, nice. However, in the other case, where now I know I don't have a C, I have either an A or a B, I still have to do a little bit more work. But I can find out a bit more information by asking, well, are you an A or a B? And it's either, so if it's left and left twice, it was an A. And that means for the output, I just need to go left once, give the A. And if on the input side it's left then right, then what I've got is a B, And to give that as the output, I need, because it's grouped differently, to go right, then left. And that's a done definition. So I will pop that in Mattermost and fling it over to Fred. Fred, you might want to stick your mic back on.
I don't know why it does that. Sorry.
No.
So let's see if we can do the corresponding logic thing, which in 106 land is called an OR gate, or it's just a proposition P or Q, right? So how do we prove P or Q? Well, this time is a little bit different because before when we wanted to prove P and Q, for example, we just had to do both, right? And we were given 2 sub-goals to do both of them. But for the OR, it's really up to us which one we want to prove. So we have to say, so there is, again, introduction, but this time there's 2 different introduction. There's the left introduction and there's the right introduction, right?
It's
the other way around.
IL and IR. Or
Uh,
introduction left.
Yeah, so or introduction left. So if I send this to ask, then it says, well, you want to prove P or Q, okay? You should decided to do it by the left introduction, then you have to prove P, right? Or I can decide to prove it by going right. Okay, and then I should delete more things before I send it, and then I have to prove Q. And how does it work the other way? So if I have P or Q, and I want to prove R, then again I can do a from.
Well, you need to do implication introduction first.
Yes, thank you. So I always do that. So now I'm given P or Q. I can do a from on this thing. And then this time I get 2 sub-goals, right? So if P is true, then I have to prove R. But it could also be the case that Q is true, and then I have to prove R, right? So because I only know that P or Q is true, right? I don't know which one it is, so I have to be able to deal with both cases. So the from here on this one looks a lot like the introduction for the and the by for this one looks a lot like the from for the and. Right? So it's dual in some sense. And again, so this time I put in the brackets just to make it clear what's going on, but it's the same kind of deal that you don't, that this binds tighter than the implications. If you don't put any brackets, then by default, it means that we are assuming the or, and then we are proving the implication, right? Rather than, so put it in a comment again. So by default, if I just write this, then that means your Q implies R. And if I instead were to bracket it like this, that's again very different. So the first one here says, well, I can deduce something from knowing P or Q. This one means that I either know that P is true, or I can deduce something from knowing that Q is true. But most of the time, this is the one that's helpful. So that's why we bracket it like this by default. So let's do this example again, which looks very similar to what Connor did.
I would comment out the
yes.
The reason for commenting it out is that Ask is always willing to make use of things you've proven earlier, even if you haven't finished proving them yet. And P or Q implies R is a very powerful result. You know, if that were true for any P, Q, and R, it would certainly be true for the thing Fred's about to prove.
Okay, so let's see if we can prove that if either this is true or that is true, where this is that either P is true or Q is true, then we have it bracketed the other way, right? Okay, so how should we do this? Well, step one is not to think, because we're proving an implication. Just going to say by implication introduction. Okay, and then now we have two moves we can do, right? We could either decide, okay, I'm trying to prove an OR of three things, which again is by default bracketed to the right. So I'm really trying to prove an OR of two things, where the second thing is again an OR. So one move we could try to do is we could just commit to one of these and try to prove it. So if we know that P is true, then we could commit to going left and proving P. But the problem is we don't know if P is true or not, right? We just know that either this is true or that is true. So I think we should do a from on this to see which case we might be in. So I'll do a from on the input. So just like before, I was trying to smash the input as much as possible to get down the pieces. Here, I'm trying to just investigate the input as much as possible so I know which case I'm in. So I say from on the thing I'm given, and then asks as well, either you're in this case, that's this line, or I'm in this case, that's this line, right? So if I'm in this case, then I actually know that R is true. So that looks good. Then I think I can commit to saying that I'm definitely going to go right here because R is on the right. So I'm going to say an OR introduction right. Okay, so then I have to prove this right-hand thing, which is Q or R. And again, I'm going to say, well, I'm going to go right. And then there's nothing more to be done because I'm given that R is true and I have to prove that R is true. Us can do that for me. So that's the easy case. In this case, I still don't know if P is true or if Q is true, right? And remember, this is bracketed like this. So again, I'm going to investigate and see which one of these cases is actually holding. And then I have two subcases. I have to be able to deal with the fact that P might be true, and I have to be able to deal with the fact that Q might be true, right? Just put these brackets back in. Okay. In this case, life is easy because my goal is to prove P or something else, and I know that P holds. So here I should just be able to say, I'm going to introduce an OR on the left. And that's immediate, right? Because I'm asked to prove P, but I'm given P. In this case, I know that Q is true, so I should be able to prove that Q or something else is true, right? So I'm going to go right. Okay, so now I have to prove the right-hand component here, but now this should be easy. I know that Q is true, and I want to prove that Q or something else is true. So that I should be able to go left. Okay, and then we are happy. And again, I'll put these comments out of the way so that we can look at these two programs at the same time. And I'll let Connor see if, say if they can see any similarities between these things.
Well, so yeah, we're in the same situation, right? In the program, the input was some possibilities grouped to the left, and what did we do? We got hold of the input that corresponds to implication introduction, and then we took it apart. That's the same. The froms in the proof and the froms in the program are doing the same job of splitting three possibilities grouped to the left apart from each other, and then the lefts and rights after the equal signs in the program are making the the exact same choices that are happening in Fred's proof. So you know, that's you know, yet another example of the tight connection between logic and programming. I mean, the idea here is that what we're doing when we're proving is that we're programming with evidence. You know, the data that we're working with is evidence for the truth of something, but we're still talking about, you know, a proof of and is a pair of proofs of the two pieces, and a proof of or is either a proof of one thing or a proof of the other thing. And you can fling them around just like data, just like numbers and strings and bits. So we're you know, programming and proof, you know, fit together. And what's going on when you write a program in real life is that you're just you're just doing the data manipulation part of some kind of explanation that might live in your head, or hopefully it lives somewhere. But you know, that's the kind of key idea of CS103, is that the programs you write come from some sort of explanation. And you know, that's really you know, how do you arrive at programs is by having some kind of model of what's going on in the situation that the kind of business logic of your program has to be about. So we're just trying to give you, you know, the reasoning toolkit in your head for building explanations that will enable you, even if you never actually do formal proofs in real life when you're, I don't know, working for JP Morgan or wherever you end up, you know, there'll always be some purpose to your program and some you know, some reasoning process whereby you convince yourself that that you're making a sensible choice of what your program ought to do. So you know, if you're wondering when will I ever use this stuff, you use it every time you decide to write a program one way and not another. Okay, let's have another example which involves perhaps both and an or. How about that? I better share my Emacs again. So let's have distribute. So suppose we have both A and either B, C. We ought to be able to get from that we either have both A and B or both A and C. Does that ring a bell? Okay. So I've got my hands on the input. And if I do from on it, I'll discover that I've got two things with badly chosen names. This is an A, and this is a Bork. Okay, but in order to give the output, I've got to commit either to go left or go right, which means I better find out what I'm playing with. So I can look, I was either on the left or I was on the right. I've chosen better names. And if my second component was on the left in the input, then I'm going to go left for the whole thing. And I'm going to give back both A and B, a pair of A and B. And if my second component was on the right, then my whole output is on the right, and that's a pair of A and C. So that's something which is not entirely unlike the distribution of multiplication over addition, but it's a program instead.
Can I ask, where did Bork come from?
Sorry?
Where did Bork come from?
It's a name I chose for the second component of this pair.
So also it's just a completely random variable.
It's not, so it's a name that I chose because it represents a value whose type is either B, C, which means it's a B or a C.
Or B or C.
Yeah. I'm pronouncing it Bork because that's it looks like it's pronounced Bork, but it's meant to be B or C. Right.
Okay.
So pop that in Mattermost and
Right. And let's see if we can do this in logic land. Right. So I'm just going to copy this. I'm going to stick a probe in front, and I'm going to turn both into and. And I'm going to turn either into or, right? And then I guess I'm going to turn A's into P's. P's into Q's. And C's into R's. Right. But there's absolutely no reason to do this. It's just a name for what I'm calling this proposition. I could as well call it A and so on. But
yeah.
When we're dealing with logic, we like to call things P, Q, and R because P is the first letter of proposition. But that's just a convention, right?
Yeah, it's like calling numbers N.
Yeah. Okay, so let's see if we can do this. So again, we're trying to start proving an implication. So there's absolutely no thinking required.
Yeah.
And then we are given an and of two things. So again, before we turn our brains on, we might as well just smash this into pieces.
Yes. So you might be getting the impression that when you've had some practice, you know what's a free hit and what you might need to think about. And implication introduction. If you see an arrow in your goal, just do implication introduction. That's just that's never a bad move. Likewise, if you have an assumption which is an and, it's always a free hit to from it, take it apart, get both pieces, because you're not making any commitments in either case.
We just have more things given to us now, right? So we used to just have this thing, but now actually we also have these two additional pieces. So but that's no bother.
By the opposite reasoning, when your goal is something or something, you really need to delay making a commitment until you know what's going on.
Yeah, because at any point here, I could just say by or introduction, left or right, right? But I really have to commit to going left or right. So if I don't know which one I want yet, then I really shouldn't shouldn't try to make a choice. And here, I don't know which one I want yet. So I know that P is true, but I don't know if I can make this true, because to do that, I also need to make Q true, or if I can make this true, because to do that, I also need to make R true, right? And I don't have Q or R in my list of assumptions here, but I do have Q or R as one thing. So I can actually look at that by doing a from on it. And then I get given two cases. Either the first one was true or the second one was true. And now I'm in a much better situation, because in either of these cases, I actually have the pieces I need, right? So in this case, I have P and I have Q. So I have P and Q. So here I'm ready to commit to saying or introduction left. And then I have to press up a proof of P and Q. But I know how to do proofs of and of things. I do an and introduction. And then I will be asked to prove P and I will be asked to prove Q, but actually these are just things that I have given. So I have no more proof obligations given to me by ask. And similarly here, I know that R holds, I know that P holds, so I should be able to prove that P and R holds, right? So this time I'm going to do an OR introduction right. Okay, then I have to prove P and R. And that's an and. So I'm going to introduce an and then the pieces are so simple that we can just pick them up from our assumptions, and there's nothing more to prove. And again, I'll let Connor compare this with that.
Yeah. So I'm hoping that you can see that we did the same thing in the program and the proof. The implication introduction corresponds to naming the input X on the left-hand side, and then we took it apart to see both of the pieces. And the second piece then is something or something, and we take that apart to see which case we're in. And at that point, we are ready to commit to whether we're going to choose a left output or a right output. And in the left case, we're giving back a pair of things that corresponds to the and introduction, and we're making use of the A and the B that we unpacked. That's the P and the Q in the proof. And when we go right, we're packing up the A and the C that we unpacked. That's the P and the R in the proof. And you can see the proof and the program are the same shape of tree. You notice the indentation is important here in the proof. So that's to say that when we are given the P on the third line, before we've split into the two cases, we still have that P in both cases after the split. You know, once you learn something, you hang on to it. And the proof can split into multiple cases, but what you already knew before you split, you still know in both cases after the split. So that's why the P is available to both the OR introduction left and the OR introduction right. So yeah, once again, same kind of situation. Right.
So in contrast, this Q is not available in this sub-branch, right? If
Correct.
I try to change this to going left again, proving P and Q, then I still have to prove Q here. It's not, I don't have that in my list of assumptions.
Yeah. So here the indentation matters, and the tree structure is crucial. It's 10-2. But so let's do another 5 minutes. Maybe I'll do a bit of proof. So I better hit share. And my editor. Right, so you've seen implication, and you've seen and an or. Any guesses what's next? Let's
Excellent.
haha, that might just show up one of these days. But there's something more before we get anywhere near XOR, we should concern ourselves with straightforwardly the idea of not. Yes. Right. So, how do you prove not P? Well, there's a rule called not introduction, which says, given P, prove false. The thing about false is a proposition that's definitely false. There's no way to prove false. At least not unless someone has already given you but the only way to prove false is if there's something wrong about P. And that's really what not P means, is there's something wrong about P. It means if P is true, then we're in trouble. Likewise, I'm going to comment that out. We can say, well, what use is it to know not P? If I want to prove, if you give me not P and we're trying to prove Q, well, okay, I'm certainly going to do implication introduction. Then how do I proceed here, right? I'm given not P. I'm trying to prove Q. I mean, maybe I know how to prove Q, in which case I would just carry on and ignore the assumption. But maybe Q is terribly tricky. So my strategy might be to throw my hands in the air and say, this can't possibly be happening to me. If I say from not P, I'm told, well, okay, fine, forget about proving Q, but you have to show that P is true. So that's to say, I'm saying the situation's impossible, but I have to show that it's impossible by proving the thing we're assuming is false. So yeah, that's can
something be neither true nor false?
That's an interesting question. You're heading for the cliffhanger. Well, what I was going to do, first of all, was to prove that if we know P, we know not P. So how does that go? Goes by implication introduction. That's not much we can do there. And likewise, if you're proving not something, then not introduction is always a free hit. Okay, so I'm given not P, and I have to prove false. Well, if I have to prove false, I'm in trouble. So I have to make sure, the way I get out of it is to say this can't be happening to me. And I use that. I do that by working from a not. So if I go from not P, that means I have to prove P instead of proving false. But I know P. So that was easy. So here's the cliffhanger. Can we go the other way around? And I think as it's 5-2, I'm just going to leave it like that. And you folk, if you want to, between now and next week, can muck around and see if that works. Anyhow, we should collect all of these things and make sure that they're available to you somewhere. I shall certainly take that much and drop it in Mattermost. Send on that. But anyhow, it's time we weren't here. I'll stop sharing my screen and just say thanks all for coming this horribly early time on this thoroughly rotten morning. And have a great day and stay safe from the storm.
Thank you.
Cheers, folks. Hopefully see you in 3D next week. And let's do good stuff on Tuesday if we can. Right? Should stop the recording, shouldn't I?